Recording in progress.
Everybody, welcome to the main talk.
So today we have visiting the Czech Academy of Sciences from the Polish Academy of Sciences, Dimitris Gerontogiannis, who will speak about the log-Laplacian on Ahlfors regular spaces and noncommutative boundary.
Thank you. Thank you for the invitation. And I should also thank Freddie for the thorough intro into the realm of spectral triples. Now, in this talk, I will not, of course, at the end, I will talk about spectral triples a bit, but I won't delve into that immediately. And I will not talk about real structures in this talk. So it will be more basic stuff about spectral triples. All right. So the idea here in this talk is that we want to extend differential geometry into less regular spaces that might not be manifolds. And we want to find the analog of a Laplace-Beltrami operator for metric measure spaces. There has been quite a lot of work in that framework, but there hasn't been work in trying to generalize the Laplace-Beltrami operator on metric measure spaces in a way that can be used in noncommutative geometry, in the sense that it will be compatible with dynamical systems and you get the notion of a spectral triple and all sorts of stuff. I will come back to this. Now, this is joint work with Bram Messeland from Leiden University in the Netherlands. And the framework I'm going to talk about is Ahlfors regular spaces. These are metric measure spaces, okay? And for the talk, we focus on a finite measure, mu. And now you want some compatibility with the metric structure. Okay, you want some compatibility with the measure and the metric structure. And it's the following. The ball around any ball of radius r, you wanted it to be of order r to the delta. And delta is some exponent. Okay, you don't want it to be equal to that. This symbol here, by this, I mean there are two constants, C1 and C2 uniform constants that do not depend on x and r, for which the measure of the ball is greater than C1 times r to the delta and smaller than C2 times the delta. Although not every metric measure space has this structure, for the purpose of noncommutative geometry is quite general. In fact, here are some examples. Any compact Riemannian manifold admits such a structure. You take the Riemannian metric and the volume measure. It's going to be Ahlfors regular, and delta is going to be equal to the topological dimension. As I write here, in general, it's going to be some sort of a fractal dimension. Okay. Now, several fractals in Rn have such a structure. In fact, the Hausdorff measure of dimension delta. Okay, you have several Hausdorff measures in a metric space, but for several fractals, there's gonna be one dimension for which this formula, this condition is true, like the Sierpinski gasket. It's one example, or fractals that are obtained as limit sets of iterated function systems, if they satisfy an open condition, it's called. Now, Smale spaces are phase spaces, the phase spaces of hyperbolic dynamical systems, where you have contracting and expanding dynamics. So they are chaotic dynamical systems. And you can equip them with some visual metric, some special metric, with respect to which the measure that maximizes the topological entropy of the dynamical system is Ahlfors regular. In the same way, you have like the Gromov boundaries of several hyperbolic groups. You're equipped with the so-called Patterson-Sullivan measure. And it's Ahlfors regular, and also the limit sets of several isometry groups of hyperbolic spaces. They have this structure. So as you see here, we will try to put geometry on all these classes of metric spaces. Okay, so I would say it's quite more broad than Riemannian manifolds. But of course, if you want to pass from Riemannian manifolds to something that doesn't have all this symmetry of a Riemannian manifold, and you just try to use the tools that you use in classical differential geometry, it's not going to work. You need to come up with new ideas. And
what would be a space that does not satisfy this?
The Ahlfors regularity. Yeah, a space like, okay. So you can take, yeah, I like this. So you can take, that's a rectangle, okay? And now you create two maps, okay, that squeeze the rectangle, make it smaller, and place it inside itself here, okay? Maybe I should make it larger, because like here. And now you have another map, let's call it I1, and you have another map that intersects these. And I2, okay? That should also, yeah. And now, depending on how much they intersect and on the size of, on the length of the smaller rectangles, you keep iterating this process, because then you can take this and place it here, you get something here, and so you get something like a Candor thing at the end. But you can choose certain lengths, and that was proved by Polycott and Weiss, I think. You can show that the box counting dimension, a certain type of fractal dimension, is greater than the Hausdorff dimension. And if you had Ahlfors regularity, these two dimensions would be the same. Okay, so you can play around and get certain fractals that don't have this. Okay, so let's go a bit back on the Laplace-Beltrami operator. Compact Riemannian manifold, Riemannian distance, volume measure, and the domain is, let's take the smooth functions. Now, this operator, it's essentially self-adjoint. What does this mean? It's an unbounded operator. It's not defined on the whole L2 space, okay? Now, on the smooth functions, you can see that it is a symmetric operator. If it was bounded, that would imply it's self-adjoint. But a symmetric operator can have infinitely many self-adjoint extensions. Essential self-adjointness tells you there is a unique one, and that is going to be the closure of the operator. It's a highly non-trivial fact to show that an operator is essentially self-adjoint. It really depends on the fine property of your space that you have the operator acting on.
So I have a question or comment. So I think the domain of the self-adjoint extension, what is the domain in this case of the extension? Is like a Sobolev space?
Yes, yes.
Okay.
That was the is it fine?
Sorry?
All good. I mean, did I answer?
No, I mean, if my question is if the domain of the self-adjoint extension is a Sobolev space, but what is the Sobolev space?
The Sobolev space. It's the one that it's the maximal domain of delta that you can have.
Okay.
Yeah. Okay.
Okay, thank you.
So now this operator has a lot of information about your space, the manifold. For instance, from its spectral theory, you can read of the dimension of the manifold. So if you take, so that's a positive operator. And if you take, but it's a compact manifold, so 0 is going to be in the spectrum. You add 1, you add something positive, and you make it invertible. So 1 plus delta to the minus t, it's a nice bounded operator. And then you ask yourself, when is it the trace class operator? Okay. And indeed, it's trace class, meaning the eigenvalues, the singular values go really fast to 0. And it's going to be trace class whenever t is greater than the topological dimension over 2. Moreover, you see the symmetry of your manifold, because if you have any isometry on your manifold, then you can view this isometry as a unitary operator on the L2 space, okay, acting on the L2 space. And so you can form this commutator whenever it makes sense, because it's an unbound operator. And you can show that for any isometry, delta will commute with a unitary operator associated to the isometry, and that's if and only if. Okay, so you see the symmetry of your manifold. But in noncommutative geometry, you care about actions often, not always, but also about actions which are not isometric. Okay. And then delta will not commute boundedly with non-isometries, typically. Moreover, delta, as it is not going to give you a spectral triple over where the smooth algebra is going to be a multiplication operators by smooth functions, because of the Leibniz rule that you have for the Laplace-Beltrami operator. So it's going to be an unbounded commutator. So the Laplace-Beltrami is not going to give you spectral triples. But nevertheless, it's a very important operator because it holds a lot of information. Now, the idea, well, the question is, can we generalize Laplace-Beltrami operator on Ahlfors regular spaces? Well, that's the first question. The second is, can we do it so that we achieve delta commutes boundedly, commutes with non-isometries? Of course, with isometries and non-isometries in general. And the answer to the first question is no. We cannot have this simply because Ahlfors regular spaces are a bit general. Depends on what you want to do with them, okay? But for this, they're a bit general. Like they have totally disconnected spaces. Some of them are like the counter sets with some ultrametric. They are Ahlfors regular. And you cannot have Laplace-Beltrami type operators on them as they are, because the Laplace-Beltrami, they correspond to local operators. They act locally. They give rise to local diffusion. Okay, and the fact that on totally disconnected spaces you have nice characteristic functions, and these are going to be in the domain operators, means that you cannot have local diffusion, so you cannot have a Laplace-Beltrami operator as it is. So it tells you that you need to look to non-local operators instead, operators where they give rise to diffusions with jumps. Okay, and this way you can have them on totally disconnected spaces. You want to ask?
Yeah, what do you mean when you say local diffusion?
Local diffusion, I mean something that an operator, very roughly, I mean you can formalize this, but an operator that if you take f function and you let the operator act on f, then the support of delta f might not be related to the support of f. The support of f might be something small, but delta f, the support might be large, so that's non-local. Local would be the support of f and the support of delta f, they're close to each other. Okay, so you can determine delta f at x by values around x. So we need to look non-local operators. And now, can we achieve these bounded commutators with non-isometries? The answer to this is yes. You need to, and that's a technique that was developed by Bram Esland, Magnus Goffeng, and Adam Rennie. You need to log dampen an operator so that it doesn't, its eigenvalues do not grow very fast. And then, but the problem is the following. You first need to have an operator to log dampen it. And as I told you, for like fractal spaces, you might not have in general. So one needs to come up with a non-local operator with slow-growing eigenvalues. Okay. And logarithmic Sobolev spaces. Well, the idea is to come up to find an operator that, in principle, behaves like the Laplace-Beltrami, and using the Rees representation theorem. So okay. So you define a bilinear form, which is densely defined on the L2 space, okay, and then using the Rees representation theorem, since E is densely defined, then you will be able to find a positive self-adjoint unbounded operator. In this case, operator for which delta, I'm using the same letter here as the Laplace-Beltrami, okay, but that's not the actual Laplace-Beltrami operator, for which its domain, for which the domain of the square root of delta, you can take square root, it's positive operator, self-adjoint and everything, gives you back the bilinear form that you started. Okay, and the domain of the square root of delta is the domain of the bilinear form. Okay, so going back, this is really a reminiscence of, no, wrong. This bilinear form really looks like a fractional Sobolev spaces. And fractional Sobolev spaces is where you, in this exponent here, delta is the Hausdorff dimension, okay? You add a small alpha, where alpha is between 0 and 1. Now, these have been studied by so many people with the fractional ones, like plus small alpha. But most of the tools do not work when you put alpha equals 0. Okay, and also if you really want to study the operators that are associated to such bilinear forms in the sense of non-commutative geometry, you really need to work hard. Okay. The reason that we call this logarithmic is because of the following: the singularity here, because that's singular. Okay, if it blows up, it's 1 over something that gets very small. The singularity, it's logarithmic. If you remove a ball of radius r, like a small ball, then the integral blows up logarithmically. And that's a weird singularity to handle. All right. So we have this unbounded operator, the self-adjoint operator associated to the logarithmic Sobolev space, and this is what we call the logarithmic Dirichlet Laplacian or log-Laplacian. Now, this can be nicely described as follows. If you take Lipschitz continuous functions, or more generally log Holder continuous functions of any exponent, or even more generally Dini continuous functions, these are functions for which the modulus of continuity is summable, basically. You can really write the log Laplacian on those functions as this integral. Okay, so that's a very simple description, I would say, and very canonical, because all the data that we started with is a metric measure space x d mu, and you end up having an operator that depends on x, d, and mu. Delta is something that comes from the metric, okay, the Hausdorff dimension of it. So that's the operator, and now I'm gonna show you many examples, just examples, okay? And so you try to convince you that it connects several areas. Okay, so first, how does it look on the Riemannian manifold? Using that's the operator on Lipschitz functions, let's say, and also Dini continuous functions, but just Lipschitz functions, fine. Now, this is really a bounded perturbation of the logarithm of the actual Laplace-Beltrami operator. Okay, so you have that delta is the logarithm of the Laplace-Beltrami plus a bounded operator. Okay, and multiple of that. Now, the way to see this is using heat trace asymptotics for the manifold. And then you really end up getting that delta. This is really coming from heat trace asymptotics. You really get that delta is C plus log of Laplace-Beltrami plus T. The bounded terms come from the part of the heat trace asymptotics that we don't care that much. What is interesting is that this C here does not depend on it. It's topological. It's the volume of the sphere of the dimension of the manifold minus 1. we don't really understand what this means, but it's there. And as you will see, we will keep getting thresholds that they're some kind of, they have topological content. Now, from this equality here, we can see immediately that delta is essentially self-adjoint on Lipschitz functions. Okay, and you get that because this is essentially self-adjoint on Lipschitz functions, and that's a bounded perturbation. So this is going to be essentially self-adjoint Lipschitz functions, and also it has compact resolvent, like 1 plus delta to the minus t to the minus 1 is compact. In fact, it's going to be the resolvent is not going to be trace class due to the logarithmic singularity, but these heat semi-groups here, like e to the minus t delta that you form using functional calculus, they're going to be compact and they're going to be trace class whenever t is greater than the dimension of x over the volume of that sphere, the dimension of the manifold minus 1. And that is sharp. Okay, so if you take t equal to that or smaller, then you don't get trace class. And this is somehow related, as I will mention in a bit, to KMS states on Caesar algebras, if you allow dynamics acting on. Or
So what's, how does K model class of this guy relate?
it's 0 so far. It's a positive operator. So far it's commutative stuff. Okay, to the other end of the spectrum, we have a manifold. Here is a counter set. Okay, take the 0, 1 infinite sequences. You put this ultrametric, basically you measure for how long 2 sequences are the same, and the moment that they are different, you pick that number and you put the distance to be 2 to the minus that number, okay? And the measure is really defined as I write there, like a ball of radius to the minus n as measured to the minus n, okay, pretty simple. Then you can actually diagonalize delta on the nose and being able to write it as that sum, so that's the spectral decomposition. And from that, this is related to wavelets, you have heard that, like through dilation and translation. Here you don't have much translation, but you have the analog of dilation. I can explain more if you want me later on. So from this decomposition, you get essential self-adjoint tensor Lipschitz functions. I remind you, it's not a trivial thing, essential self-adjointness. And you also have compact resolvents, and the heat operators are trace class whenever t is greater than 2 times log 2. Now, of course, you can do this in more general shift spaces. What you will end up getting there is the topological entropy of the shift space. So log 2 is the topological entropy of the shift map. Okay, so still something topological. This threshold of when the heat operators are trace class or not has some say topological volume. It tells you how large the system is. Okay. Now you might wonder, why do we care about something, an operator that gives you a bad heat kernel? Well, you cannot have everything in life. Because we want to use this operator in dynamical systems, okay? And it turns out if it had a very good kernel, it cannot be compatible with non-isometric actions. So you give something, you say, okay, bad kernel, but for small t, and then you gain compatibility with dynamics. Another example, the unit interval. Okay, so you might wonder the unit interval. Okay, of course, we know everything about the unit interval. Well, that was not very obvious to us, to Bram and me, because the unit interval is the closed one. And the Laplacian, the actual Laplacian, is not self-adjoint there because you have boundary conditions. It turns out here you don't have a problem with this log-Laplacian. Okay. In fact, one can diagonalize it on the nose, and using this very, very simple high school, well, not even high school, junior high school rule, okay? Because that's the formula, you recall, right? So you evaluate delta at x to the n minus y to the n, and the distance is the distance of x minus y on the interval, okay? So you break the interval to two parts so that you make the distance go away, and you can just cancel the terms. And then you end up getting this recursive formula, like the first eigenvalue is 1, and that's an eigenvector. The second eigenvalue is 3 over 2, 11 over 6. Can you make a guess what these numbers are? Huh? Sorry. So they are the harmonic numbers. 1 by 1. Well, 2 times that, but that's irrelevant. It depends how you build the metric. Okay, so you get all the harmonic numbers, and these are the eigenvalues, and they are simple. And the eigenvectors are the Legendre polynomials. That was not unexpected to get something like Legendre polynomials, but to get the harmonic numbers on the nose, that was like, what's going on here? Because you only have an integral, and you don't have any harmonic numbers. And this comes from the logarithmic behavior. But to get them on the nose, yeah, I don't know. So that's the unit interval. Now, compact groups, not necessarily Lie groups, okay? No smooth structure. Of course, you can have smooth structure, but it's not necessary. For instance, you can take solenoidal groups, which are fractal type. Okay, and you can have the Laplacian. So assume X is a group, you have a bi-invariant metric, and you take the Haar measure. Then delta is going to commute with a convolution on the group. If you take 2 functions, Lipschitz functions, let's say, and you convolute them, okay, then you're going to have this. Is equal to a okay, but you also have that this is equal to this. So in fact, delta is also an unbounded multiplier for Caesar algebra. Now, these properties really tell you that on the Peter-Weyl decomposition of the L2 space of your group, after using Schur's lemma, you have that, because it commutes with a convolution, you have that delta acts by scalars on the decomposition. So it's a Casimir type operator. So it generalizes. Yes, yes, but it's not Lie. That's what I'm saying. So, yeah, exactly. And also, you obtain essential self-adjointness on Lipschitz functions, okay, from this decomposition. Okay, so it acts nicely your groups, and here are some general facts about the log-Laplacian on Ahlfors spaces. Indeed, we always have compact resolvents, and the eigenvalues grow logarithmically fast, as we wanted them to be. The domain of delta, it's a nice domain, quite large. It contains every Holder continuous function in it, so it's pretty large. And the commutator of delta with any multiplication operator by a Lipschitz or Holder or Dini continuous function more generally it's going to be a bounded operator. Okay, and in fact, an integral operator. In fact, the Calderon-Zygmunt operator. And that's pretty nice.
Should I ask?
Operator?
No.
No.
Yeah, nice integral operator. So, and the last property, it's quite remarkable because of the following. So you take the domain, like that's the smooth functions, okay? That the delta smooth functions, okay? You have all Lipschitz functions are smooth. That's weird. But I have an explanation. Because here's what's happening. If you have a manifold, like a smooth structure, and you consider the Lipschitz functions, almost everywhere they're going to be C1, the Lipschitz functions. So you would expect them not to be C infinity. But somehow delta, this means delta is of very, very low order. In fact, as an operator. In fact, it's should be thought as an operator of order epsilon for any epsilon positive. Okay, not 1, not 2, it's almost 0, so it's almost bounded, but it's unbounded.
This is despite the fact that you have a difference between compact line and manifold. Delta is not the same thing as delta.
Exactly, it's the logarithm of that. But you can prove it in the metric measure space framework. And I can go back to this example, and you see here, delta takes a polynomial of degree n, it spits out a polynomial of degree n. So it doesn't reduce the order.
And are these operators diagonalizable?
Yes. Yes. So you mean it's self-adjoint?
Yeah. Okay.
But what is not clear is if you can find a nice collection of eigenfunctions. That's highly not clear in general. And in all the previous examples, you were using the group structure, let's say, or the niceness of the manifold, or the niceness of the ultrametric space and stuff like that.
Yes, sure.
Exactly. So indeed, well, I can skip that because we have seen spectral triples for this talk. It's a triple where you have a Hilbert space, and A is a subalgebra of the bounded operators on H. D is a self-adjoint operator acting on H with compact resolvent, and you also want a smooth subalgebra of your Cicer algebra that preserves the domain of your operator, and the commutator extends to the bound operator. Because I'm saying extends because first you need to make sense of it, wherever you can make sense of it, and then you can extend it. All right, and here's the corollary of the previous slide. For any Ahlfors space, you consider the log-Laplacian, and you get this spectral triple. You have like the Lipschitz functions or Dini functions as your smooth algebra. Okay, and the Hilbert space is the L2 space of X with the measure mu. I forgot to write it down. Mu, and delta is your abstract Dirac operator. And this gives you a spectral triple, but the k-homological content is 0 because it's positive. That's not a bad thing. And it should be expected because it's you try to create an analog of Laplace-Beltrami operator. But now we can go to a more interesting stuff. How can we use this in dynamical systems? There delta on limit sets of Planian group. So what's a Planian group? You take the unit ball in Rn plus 1, and you equip it with a Poincare metric, and then the ball becomes a model for the hyperbolic space. Now its isometric group, of course, acts isometrically on the ball, but its extension to the boundary of the ball, which is the sphere, is no longer isometric. Okay, but it's still by diffeomorphisms, and the action is controllable enough. It's conformal, one would say. And on that ball now, you can see the behavior of somehow you can study discrete subgroups of this isometric group of the hyperbolic space. And how can you build them? Well, you take any discrete subgroup of the isometric group. Okay, you have some conditions. It's not important for now. I don't want to dwell on that. And then you can create a fractal on the unit on the sphere, on the boundary of the hyperbolic space, as follows. You take an element in the hyperbolic space, so in the unit ball. That element is x here, and then you take its orbit under the discrete group action, and this is going to move around, but then it will accumulate the boundary. Okay, and this is going to be your fractal. It's not always going to be a fractal, but typically it's a fractal. And on that limit set, you can have the chordal distance, because it's a subset of the sphere. So on the sphere you have the chordal distance. You just restrict that distance on the subset, on the limit set, and you have a nice measure, the Patterson-Sullivan measure. And that's a picture of a limit set, and we have differentiation on these structures. But not just on this structure, but also with the Kleinian group acting on that. So the differentiation of this structure is compatible with the action of the Kleinian group, which is not isometric. Being isometric or non-isometric really tells you, well, non-isometric action increases the chances for the commutator to be unbounded. Okay, and having bounded commutator really tells you that, very informally speaking, if you have a bounded commutator with a function, means that f is delta differentiable. Okay, and now if you have bounded commutator with a unitary of an isometry, of a homeomorphism in your space, means that gamma is delta differentiable map between the differentiable space, the smooth space. Okay, and indeed that is true. The commutator stands to a bounded operator, and you obtain a spectral triple on these cross products. And the niceness of those is that they are intrinsic. We haven't made any choice to construct the spectral triples. Usually the way of constructing spectral triples has been, you find an interesting orthonormal basis for your Hilbert space, and then you try to create a diagonal operator by putting the right eigenvalues that do the job. But here it goes the other way. You simply start from a metric measure space, and you get a spectral triple for dynamical systems. And as it is, it's still a positive operator, has zero topological content, but you can add potentials and obtain Hamiltonians. And these will not have trivial topological content. And I think I have like 10 minutes. So I will go now to another example that could have been a separate talk on its own, but I will just skip through and I will just try to give you the big picture. This is joint work with Bram and also Magnus Goffek from Lund University in Sweden. And that's another example where we construct spectral triples on Caesar algebras associated to topological Markov chains. Okay, so topological Markov chains are dynamics on totally disconnected spaces, so far from being classically smooth. But nevertheless, it's possible to do harmonic analysis, as you see here. I write Higg operators. You can actually compute them on the nose. And also view these non-commutative, actually non-commutative Caesar algebras associated to the topological Markov chains as manifolds, non-commutative manifolds, as Freddy was describing before, using the Gelfand duality picture. And so, you know, you have the duality between compact Hausdorff spaces and commutative unital Caesar algebras. And then you're asking, okay, is there a duality that also sees the differential structure if there is one? And yeah, so I don't want you to really digest what's going on here, but the idea is the following. We start with a finite directed graph. And on this graph, any two vertices can have up to one edge. Okay, well, let's reduce it to that. And since you're on a finite directed graph, you can start talking about paths, finite paths. Okay, you start from a vertex and you just walking. And the assumption is that the path is very connected. So any two vertices can be, between any two vertices, there is a path connecting them. But we assume it's strongly connected, meaning that there is a uniform length, L, for which any two vertices can be connected by a path of length L. Okay, and now you can consider this product space. Actually, the symbols or the vertices are the numbers 1 up to n, and then you consider infinite words. Well, so these are infinite paths, okay, on your graph. You can also have infinite paths. And you have an adjacency matrix telling you when you can concatenate two symbols. The matrix can be, this matrix has only 0 or 1 entries. If it has only aces, then you don't have any restriction. If it has some zeros, then you need to be careful. And then you have the shift operation where you just shift to the left. And again, you have a nice measure. Okay, and then this becomes an Ahlfors regular space. Now, on this structure, you can associate a Caesar algebra. There are several ways to, well, a couple of ways to construct this algebra. Okay, so you start with partial isometries, SI. Partial isometries, you can view them as being the analog in Caesar algebras of local homeomorphisms on the space. And then you generate star algebra out of those satisfying these relations that I write, and then you take a completion to create a Caesar algebra. The first one, so these are all projections in a Hilbert space, and you want them for any vertex. I mean, yeah, to decompose the identity, and then you also want them to be mutually orthogonal, and moreover, you want the source projection, because these are partial isometries. So each one gives you two projections, the source projection and the range projection. And you want the source projection at I to be given in terms of the range projection of the vertices associated to I, that I can move to. And the NCG of those Caesar algebras indeed was studied before by Goffin, Meslin, and Rainey, but in a more algebraic way, and building spectral triples using bases and picking the eigenvalues. But using the log-Laplacian, after understanding the log-Laplacian for metric measure spaces, only then it was possible to really push the NCG on those Caesar algebras from a semi-classical point of view. Okay. And to get access to these Caesar algebras, because they're algebras, okay? You don't have points. And if you want to do some classical or semi-classical analysis, it's good to have some points, okay? So there is a construction, there's a structure called the groupoid. Groupoid is generalizes groups and equivalence relations at the same time. And here, and you have partial multiplication in the groupoid, it's not between any two elements. And the groupoid is really a set on which you have this partial multiplication. And it really consists, put, for instance, n equal to 0. And then you focus on infinite sequences, x and y, n is 0 for now, so that there is some k that they become the same. So they are tail equivalent. And now you let n to be whatever, they are tail equivalent with some lag. Okay? And you have this partial multiplication here, partial, because you want the last entry to be equal to the first entry, and then only then you can compose, otherwise, no. And you can equip this with a nice topological structure. And long story short, the generator Si of OA corresponds to a convolution operator on the groupoid, because on groups you have convolutions, on groupoids you also have convolution, and this gives you a more analytic flavor. Okay, and now you get more access to you get access to the more geometric aspect of Kunz-Krieger algebras. Okay, and indeed, so this groupoid contains inside the shift space SA, on which is a metric measure space, a classical one, on which we have the log-Laplacian. Okay, so the shift space is inside the groupoid. And now the groupoid can be seen as a structure that has all the dynamical phases of the shift space. Okay, like, very roughly, think of it as a cylinder, and every section is tells you something about sigma A. Okay, so it has all the dynamical behavior of sigma A, so it's quite large thing. Nevertheless, you can lift the log-Laplacian structure from sigma A to the groupoid, and indeed you end up getting the same integral formula there. Okay, so it's the log-Laplacian on the groupoid. And this construction is not very random because we really get classical behavior out of this log Laplacian on the groupoid. Indeed, you can diagonalize the log Laplacian on the groupoid, and the eigenfunctions are going to be like hard wavelets. So that's really good. And the eigenvalues can be computed on the nose, and because the construction is canonical, they give you insights on the connectivity of the graph. And they're given in terms of the transition probabilities in the graph, like what's the probability of jumping from one vertex to the other, and it has all this information. It's eigenvalue. Okay, that's nice. But what is even nicer is that you can actually compute, you have a closed formula for a hit kernel on the groupoid. This really happens in Euclidean spaces or the hyperbolic spaces, like the hyperbolic space, have actual closed formulas. Like for manifolds, you only have like asymptotics. But here you get a closed formula. And it's given like that. And turns out then that the hit semigroups, this is a probability, a transition probability for a random walk on the groupoid. Okay. And you also get some connection out of that with some potential theory that wasn't expected. I mean, you compute, you get that. So yeah, that we didn't expect this rigid. What's the word, like, to get all this structure. Okay, and now you don't only get the spectral geometry of your dynamical system and of the groupoid, like in other words, of the Kunz-Krüger algebra, something that it's not a classical space, it's a Caesar algebra. Okay. But now you have non-trivial k-homological content by considering Hamiltonian type operators. The idea is the following: delta is a positive operator, and being only positive or negative, the k-homology is going to be trivial. So you add the potential, it's an unbounded potential, and it's not a random choice. And then indeed you end up getting a spectral triple for your Kunz-Krüger algebra, and the smooth algebra is locally constant functions on the groupoid. And this spectral triple, the k-homology class of it corresponds to the class of the unit of the k0. So what do I mean is that, as Freddy was saying, it's nice to have some Poincare duality. For us here, it means that you have an isomorphism of K0, the K0 theory of OA transpose to the K1 homology of OA. Okay, this is an isomorphism. And now, one class in here is the class of the unit in OA. Okay, that's a unital algebra. You take the class of the unit in there, and this is the class of the spectral triple. It's the class of the Hamiltonian coming from the log-Laplacian. And you can do even more. You can change the potentials and get all the other classes of K0. Okay? So it's pretty descriptive, this log-Laplacian. And finally, you can, as I told you, and Freddy told you, NCG is a way, tries to view Caesar algebras as non-commutative manifolds. in that spirit, we did all this work for Kunstgerger algebras. And in particular, we know that in a Riemannian manifold, the diffeomorphism is isometric if and only if it commutes with the Laplace-Beltrami operator, the actual Laplace-Beltrami. And in that spirit, one can consider all the automorphisms of the Kunstgerger algebra that basically commute with the Hamiltonian coming from the log-Laplacian, with the spectral triple that I described to you. There is a formal way to say when this commutes, okay, and you need to involve some unitary operators. But we didn't expect that either. It's really possible to compute this group, this isometric group of this spectral triple, and show that it's a compactly group isomorphic to this semi-direct product. So Aut A is the automorphism group of the directed graph. So all the permutations that you can have that respect the graph structure. And you can act on the n torus by permuting the entries of the n torus. You view the n torus as a diagonal matrix with entries in T, in just circle, and Aut A permutes the entries. That's, I would say, a non-trivial statement to make, a non-trivial computation. It really uses the fact that there is a good understanding of the spectral theory of this operator. And yes, so you get this. And another sanity check that this should be isometries on your non-commutative manifold is that, well, on a metric space, isometries have zero topological entropy. And this is indeed true in this non-commutative setting. There's a notion of topological entropy and it's zero. And that's the conclusion. We get a spectral triple on OA with geometry, spectral geometry strongly related to the dynamics, a closed formula for the heat kernel on the groupoid, gives explicit description of the K-homology group by Hamiltonian type operators and isometric group. Thank you.
So, to your questions from the audience.
The previous page, you have this very interesting result about the isometry group of them.
Yeah.
Yes. So, is there a way to keep track on how this isometry group changes when we change a graph? By changing a graph, I mean by adding edges and subtracting edges.
About that.
So because if you start, for example, you said that you have an assumption about the topology of a graph, like you have only one edge coming out.
Yeah, but up to topological conjugacy, if you have like multiple edges, you can just increase the size of the graph and make them the GC matrix to be 0 or 1. So it's a vertex. See? Yeah, but sorry.
Yeah, I was just wondering if you start with, if you construct a graph inductively, if you start with just discrete set of vertices and keep adding one edge at a time, like keep track of it.
I don't know. That's interesting though.
Okay,
I don't know.
Also, you had another very interesting example.
I can add something. I can add something to that. So here, I say that we have this operator D, but also we have analog d beta, where beta is any finite path in your graph. Okay, so it's any finite path in the graph. Now the isometric group of D, it's so the isometry of D is this. the isometry group of d beta, where beta is an infinite path, turns out to be this. So all the permutations that fix the finite path. So it sees that.
The trivial case from beta is in the following, like trivial path. Can I ask another one, please?
Yeah.
Yeah, so you had this example with the Laplace operator on the closed unit interval.
Yes.
Yeah, so if you take two copies of this closed unit interval and glue at the this one, this harmonic numbers here. So if you take two copies of this and glue at the boundary points to make a circle, so is there a way to relate it to the genuine Laplacian on the circle? Like just take two copies of this and do something with this to see how it's related to the genuine Laplacian.
You break the topology in that way. You say that take this and assume that 0 and 1 are the same.
Or rather, take two copies of this.
Take two copies.
And glue at the
okay, I
0
see.
to 0, 1.
Okay, I don't know. Interesting. I even so like, can you do the same for the square? For cubes? Do you have something similar? No. So, and also, why do we get the harmonic like on the nose? Okay, get something. Maybe we should get something with. We should definitely get something with logarithmic growth because it's the log Laplacian. Why do we get the harmonic numbers on the nose? I mean, are they hidden in this integral form? I have also many questions about that. Probably you can also. I mean, I think this is generalizable a lot, but I don't know how. One tricky part is the following. So here we have a measure and a metric. Okay. Now the measure you can, and also how does it behave with products? If you take products of spaces, and the Laplacian, is it going to be the direct sum or? I don't know. I maybe not, but maybe you can write it as a tensor of the other Laplacians plus something bounded commutator. The problem is that okay, the measure you can take product measures, but here, if you take a product metric, like the maximum of two metrics or the sum of two metrics, you divide by those. So it's not clear what algebraic manipulation you need to do what I'm saying is that take the Laplacian on X and on Y. So what is the Laplacian on here? It's not clear. I don't expect it to be the tensor of the two Laplacians.
This kind of addresses what you mentioned before. You said when you consider the product.
The products?
Well, I mean, the reason why you start
with the 0, 1, yes, exactly, yes.
Do you have other questions?
So at the very end, you were saying that this might serve as a blueprint for more general groupoids. Can you say something about what classes of groupoids you're considering?
First, I would say that it was very involved already for the Kunze-Krüger algebras. At the end, it's rewarding. You get nice results. I believe it's generalizable to graph higher rank graphs, and so like graph situations, but not only there, because as you see here, you can go outside of the zero-dimensional situation. The zero-dimensional situation is nice because you can do computations. But you also, like, you can do similar stuff for this kind of cross products, and this can have like topological dimension, whatever. It might not be totally disconnected. Can happen if you work with Schottky groups, but in general, no. So you can have them, but yeah, we haven't done it for these cross products, like all this K-homology stuff, but it feels that it's possible. And also the idea is to go to hyperbolic dynamical systems more generally, like small spaces. And in principle, it should be possible to go to more general groupoids. Maybe one could abstract all these constructions to étale, and not only étale groupoids, but no, not necessarily. You don't need the smooth structure, but it would be nice if that generalization, in the case that you have a smooth structure, gives you something back that something nice. I mean, you need some. You want to build the theory, and don't want to be detached from something. Yes. So.
I'll ask a question then. So yeah, I was going to ask what beat me to it. But yeah, okay. So if you take one of the simplest examples of a graph C-star algebra, which is the Padlish here, I mean, it's the unitization of the compacts. Would it work there?
Don't know.
Yeah,
it's open for
people to look at.
People to look at.
Because I mean, this thing already has a very canonical spectral triple. It's been around for 20 years. So if you could recover this, that would be extremely interesting. Another question is, so associated to any spectral triple, you have an associated differential graded algebra, it's differential calculus. What does that look like in even the classical case of compact Riemannian? Do you recover the derived complex of this thing?
I say it too many times, don't know, and don't usually say that.
Okay.
But
I mean, it's there because it's associated to spectral triple.
It's there.
But I mean, you haven't sat down and tried to calculate the percent.
No, and it's not something trivial. So the first thing I would try would be to check what you said in this example, the zero-dimensional case. Do it for the Cantor set. Okay, you know the diagonalization, you know how to deal with the commutators, the one forms, and everything. Still can get very involved. Definitely, you will get something new, like on the Cantor sets. It's not clear. Another thing that one can look at now is also like using the work of Adam Rennie and Bram Esland on curvature. This makes sense. So you can try to compute the curvature. But there are things that new, so everyone is invited to, yes, to join the party.
And then another question is would you perhaps start from a Dirac operator instead of the Laplacian?
To get something even.
Yeah.
So yes, but you wouldn't get like this compatibility with dynamics probably. So there is a way, and this is related to the work of I will pronounce the names wrong, but Cipriani, okay, and Chavajot. Was it correct? Okay, good. I mean, their work is about local diffusion and Dirichlet spaces, but in this situation, a similar thing can be done, and you can decompose this Laplacian into this derivation, dd star. And then you can make sans open operator like that. And in principle, it should give you a spectral triple for commutative situations. But adding the dynamics in it, things get hairy. But if you also have a canonical candidate for spectral, even spectral triple on the counter set and stuff, a canonical one, because there are examples of spectral triples, but I wouldn't say they are canonical. There are too many choices going on. This could also be related to the gap labeling conjecture, or useful for.
Okay, thank you. So do we have any other questions from the audience or online? If you're online and you have a question, just unmute yourself. Go for it. No? Okay, that doesn't appear to be the case. So we'll thank just again.
Thank you.
Log will be Ghana. Could we have Steva from Ljubljana University Institute of Mathematics and Physics, and I think we don't have quite graphs.
Oh, we do. The relating ample and bias.
Sorry, the relating ample groupoids and topological categories with Boolean restriction and range semicolons. So we hope to see what that.